Right now, something is passing through our solar system that doesn't belong here. Not a comet from our distant ice fields, not an asteroid from our belt between Mars and Jupiter. Something from another star system entirely. It came from the darkness between stars, travelled for millions of years, swung past our sun, and is leaving forever. We call it 3I Atlas. And for a brief moment in cosmic time, we got to watch a visitor from somewhere else pass through our neighbourhood. If this kind of peaceful cosmic wonder brings you calm, please tap that like button and subscribe. We're building a community of people who love falling asleep to the universe's quiet mysteries. Where are you listening from tonight? What time is it where you are? Drop a comment and let me know. The I in 3I Atlas stands for interstellar. It's the third interstellar object we've confirmed visiting our solar system. The first was Oumuamua in 2017, designated 1I. The second was 2I Borisov in 2019. Now we have 3I Atlas, discovered in 2024. Each one a traveller from beyond, each one passing through on a journey that started somewhere we can't even identify with certainty. Atlas is the telescope system that spotted it. Asteroid Terrestrial Impact Last Alert System, a network of telescopes in Hawaii and Chile that scan the sky looking for objects that might threaten Earth. They weren't looking for interstellar visitors. They were looking for dangerous asteroids. But on one particular night, the automated system flagged something unusual. An object moving wrong, moving too fast, moving on a path that didn't fit anything from our solar system. Astronomers know immediately when something is interstellar by its orbit. Objects from our solar system follow elliptical paths, ovals around the sun, bound by gravity. They orbit repeatedly, trapped in the sun's gravitational well. But interstellar objects follow hyperbolic trajectories. They come in on one side, curve around the sun, and leave on the other side. The path is open, not closed. One visit, then gone forever. 3I Atlas is following a hyperbola. Its path through our solar system is a one-time curve that will never repeat. The sun's gravity bent its trajectory slightly, pulling it into a gentle arc, but not enough to capture it. Not nearly enough. The object is moving too fast. It came in with so much velocity that our sun, massive as it is, could only nudge it slightly before the visitor escaped back into interstellar space. This velocity is the signature proof. Calculate the speed needed to orbit the sun at 3I Atlas's distance, then compare it to the object's actual speed. The actual speed is higher, much higher. That extra velocity, that excess beyond what solar gravity can hold, proves the object came from somewhere else, with momentum our sun didn't give it. It arrived already moving fast, carrying energy from whatever event ejected it from its home system millions of years ago. The shock of this discovery never quite fades, even though we've now found 3 interstellar visitors. These objects prove that solar systems leak. They prove that matter moves between the stars. They prove that the galaxy is not a collection of isolated islands, but a connected system where debris travels from star to star, carrying material across light years of empty space. Before 2017, this was theory. We suspected interstellar objects existed. We thought they probably passed through our solar system occasionally, but we'd never seen one. The discovery of Oumuamua changed everything. Suddenly, theory became observation. The interstellar visitors were real, and once we knew what to look for, we found more. 3I Atlas is small and dim, we can barely see it even with powerful telescopes. It reflects very little light. This tells us it's either very small, maybe a few hundred meters across, or very dark, or both. Most likely both. A small, dark chunk of rock or ice tumbling through space. Invisible except for the brief period when it passed close enough to our sun to be illuminated and close enough to Earth to be detected. The object is moving at roughly 30 kilometers per second relative to the sun. That's 108,000 kilometers per hour. At this speed, you could travel from Earth to the Moon in less than 4 hours. But 3I Atlas isn't going to the Moon. It's going back into the vast darkness between stars, carrying with it the brief warmth it absorbed from our sun, returning to the cold that will last another million years until it happens to pass near another star. For a few months, this visitor from elsewhere was ours to study. Telescopes around the world turned to observe it. Every observation mattered because the window was closing. Where did 3I Atlas come from? This is the question that haunts every astronomer who studies it. We can trace its path backward through space, calculating where it was years ago, decades ago, centuries ago. We can point to a direction in the sky and say it came from there. But the actual star system that ejected it, the actual sun it once orbited, remains unknown and will probably stay that way forever. The trajectory points toward a region in the constellation Ursa Major, the Great Bear. Somewhere in that direction, between 5 and 50 light-years away, there's a star that this object once called home. But that's an enormous volume of space containing hundreds of stars. We can't narrow it down further because 3I Atlas has been traveling for so long that tiny uncertainties in its current path multiply into huge uncertainties about its origin. Think about it this way. Imagine trying to find where a piece of wood floating down a river came from. You can see which direction the river flows from. But did the wood fall from a tree on the bank a mile upstream? 5 miles? 10? Did it wash in from a tributary? The further upstream you trace, the more possibilities branch out. 3I Atlas has been traveling for millions of years. Every small deviation, its path over that time makes the origin point less certain. The journey took at least 1 million years, possibly 10 million, possibly more. We can estimate this based on its speed and the distance to nearby stars. At 30 kilometers per second, crossing even 1 light-year takes about 10,000 years. The nearest stars are 4 light-years away. More distant stars could be 10 or 20 or 50 light-years away. The math stretches into timescales that dwarf human history. This object was already ancient when it arrived. It left its home star system before Homo sapiens evolved, before Neanderthals, possibly before the genus Homo existed at all. While this rock was crossing the emptiness between stars, life on Earth was evolving, changing, adapting. Entire species rose and fell. Continents moved, ice ages came and went. And through all of that, 3I Atlas was traveling silently in the dark. How did it get ejected in the first place? Planetary systems are violent during formation. A young star is surrounded by a disk of gas and dust. Gravity pulls this material together into clumps. The clumps become asteroids, then planets. But not everything becomes a planet. Leftover debris gets flung around by the gravity of the forming planets. Most of this debris stays in the system, settling into asteroid belts or comet clouds. But some pieces get accelerated to escape velocity by close encounters with giant planets. Jupiter and Saturn have ejected countless objects from our solar system. Their massive gravity acts like a slingshot. A small object on the right trajectory can swing past a gas giant and gain enough speed to escape the Sun entirely. The same process happens around other stars. Gas giants there eject debris that becomes interstellar wanderers. 3I Atlas was probably one such piece of debris, flung away from its home by a planet's gravity billions of years ago. Or it could have been ejected by stellar interactions. If two stars pass close to each other, they're combined. Gravity can disrupt planetary systems, throwing objects into interstellar space. Binary star systems are common in the galaxy. Close encounters between stars, while rare, happen over billions of years. 3I Atlas might be debris from such an encounter, a piece of a planetary system torn apart by passing stars. We'll never know for certain. The origin is lost to time and distance, but we know it came from somewhere with a star, somewhere with planets, or at least planet-forming material, somewhere in the galaxy's vast collection of solar systems. This visitor connects us to that unknown place. For a brief moment, matter from there passed through here. Two star systems, separated by light years of empty space, touched through this small exchange of rock and ice. The object carries no markers, no signs of its origin beyond its trajectory and composition. It's anonymous, a wanderer without a home address. But it exists, and that proves something important. It proves that matter travels between stars. It proves that the galaxy mixes itself slowly over cosmic time. It proves that we're not as isolated as we might think. The space between stars isn't an absolute barrier. Things cross it. Things like 3I Atlas, carrying material from one stellar neighborhood to another, connecting the galaxy in ways we're just beginning to understand. Somewhere out there is a star that doesn't know it sent us a visitor. Around that star might be planets unaware they lost a small piece of their system millions of years ago. And here we are, briefly witnessing that lost piece on its endless journey through the dark. What does 3I Atlas actually look like? The honest answer is, we don't know with certainty. We've never seen it up close. We can't resolve its shape with our telescopes, because it's too small and too far away. What we have are measurements, brightness readings, reflected light analysis. From these, we build a picture, but it's incomplete, like describing someone's face from their shadow. The object is dark, very dark. It reflects only about 4% of the sunlight that hits it. For comparison, charcoal reflects about 4% of light. Fresh asphalt reflects about 7%. 3I Atlas is darker than asphalt, darker than most rocks on Earth. This darkness tells us about its surface composition. Dark surfaces mean carbon-rich materials, or possibly ice that's been exposed to cosmic radiation for millions of years. Cosmic radiation does strange things to ice over long timescales. Pure water ice is bright and reflective, like snow, but bombard that ice with high-energy particles for 1 million years, and it changes. The radiation breaks molecular bonds, creates new compounds, darkens the surface. Organic molecules form tars and complex carbon chains that coat the ice in a dark crust. This process happens to comets in our own solar system's distant reaches. 3I Atlas has been exposed to interstellar radiation for far longer. Size estimates come from brightness. If we know how much light hits the object and how much it reflects, we can calculate its size. The dimmer it is, either the smaller it is or the darker it is, or both. Based on observations, 3I Atlas is probably somewhere between 200 and 500 meters across, roughly the size of a few city blocks, small by planetary standards, but still massive by human standards. If you stood on its surface, it would extend to the horizon in every direction. The shape is uncertain. Is it spherical, elongated, irregular and lumpy like most asteroids? We have hints from how its brightness varies over time. If an object is elongated and tumbling, its brightness changes as different faces point toward us. A sphere would maintain constant brightness. 3I Atlas shows some brightness variation, suggesting it's not perfectly round. It's probably irregular, a chunk rather than a ball, tumbling slowly through space. Does it have a tail like a comet? This was a major question when it was first discovered. Comets develop tails when they approach the sun because solar heat vaporizes ice on their surface. The vapor and dust stream away, creating the characteristic tail. 2I Borisov, the second interstellar visitor, had a clear cometary tail, but 3I Atlas showed minimal tail development, if any. Either it has very little ice, or the ice is buried under a thick crust of dark material that insulates it from solar heat. The color gives more clues. Astronomers measure color by comparing brightness at different wavelengths. Red objects reflect more red light than blue. Blue objects do the opposite. 3I Atlas appears slightly reddish, similar to many Kuiper Belt objects in our own solar system. This reddish tint comes from organic compounds on the surface, the same radiation-created tars that darken it. The color links it chemically to objects we know, suggesting that planetary formation produces similar materials around different stars. Spectroscopy reveals composition. When sunlight reflects off an object, certain wavelengths are absorbed by molecules on the surface. These absorption features create a unique fingerprint for different chemicals. Scientists pointed spectrographs at 3I Atlas, splitting its reflected light into a spectrum. The spectrum showed absorption features consistent with silicates, rocky minerals. Some data suggested possible carbon compounds, but the object was too dim for detailed analysis. Much of its composition remains guesswork. The surface is probably rough and battered. Millions of years in interstellar space means countless impacts from tiny dust grains moving at high relative velocities. Each impact chips away atoms, creates small craters, pulverizes the surface layer into fine dust. The object likely has a regolith, a layer of broken, powdered rock covering whatever solid structure lies beneath. This regolith would be ancient, undisturbed, except by micrometeorite impacts, a surface shaped by eons of slow erosion in the void. If you could somehow visit 3I Atlas, you'd see a dark, irregularly shaped rock tumbling slowly against the stars. The surface would be rough and dusty, covered in tiny craters too small to see individually. No atmosphere, no sound, no light except what the distant sun provides. And out where 3I Atlas is now, the sun appears as just another bright star. The rock would be cold, far below freezing, barely warmed by the brief passage near our sun. It's a humble object, not spectacular, like Oumuamua with its mysterious elongated shape and unusual acceleration. Not obviously cometary, like 2I Borisov with its bright tail. Just a dark, small rock doing what rocks do, existing, persisting, traveling. But this rock came from another star. That simple fact transforms it from mundane to extraordinary. An ordinary rock on an extraordinary journey, briefly visible to our telescopes, before vanishing back into the darkness from which it came. The speed of 3i Atlas is difficult to grasp in human terms. Numbers like 30 kilometers per second feel abstract until you translate them into familiar contexts. 30 kilometers per second means the object travels 30,000 meters every single second. In 1 second, it covers a distance longer than 300 football fields. In 1 minute, it travels 1,100 kilometers, roughly the distance from New York to Denver. In 1 hour, 108,000 kilometers, nearly 3 times around Earth's equator. This velocity is what proves beyond doubt that 3i Atlas is interstellar. The Sun's gravity creates specific relationships between orbital speed and distance. Objects closer to the Sun must move faster to maintain stable orbits. Mercury orbits at 47 kilometers per second, Earth at 30, Neptune at just 5. These speeds are precisely what gravity requires at those distances. Too slow, and the object falls inward. Too fast, and it escapes. 3i Atlas is moving too fast for its distance from the Sun. When it passed Earth's orbital distance, it was travelling at roughly 30 kilometers per second, but not in an orbit. It was passing through, heading outward. At that distance, orbital velocity is 30 kilometers per second, but only for motion perpendicular to the Sun. 3i Atlas was moving outward, away from the Sun, with significant velocity. This outward component, this extra speed beyond what solar gravity could give it, proves it came from elsewhere with pre-existing momentum. Think of it like throwing a ball. If you toss a ball upward on Earth, gravity slows it down. The ball climbs, decelerates, stops, then falls back. But if the ball is moving fast enough, if it exceeds escape velocity, it never comes back. It climbs forever, getting slower as gravity pulls, but never slowing enough to stop. 3i Atlas is that ball, moving faster than the Sun's escape velocity for its current distance. It will slow as solar gravity pulls, but it will never stop. It will never return. Escape velocity from the solar system varies with distance. Near Earth, you need about 42 kilometers per second to escape the Sun completely. Further out, the required speed is less because the Sun's gravity weakens with distance. By the time you reach Neptune's orbit, escape velocity drops to about 7 kilometers per second. 3i Atlas is beyond Neptune now, still moving well above escape velocity for that distance. Solar gravity is barely touching it anymore. No human-made object moves this fast relative to the Sun. Our fastest spacecraft, Voyager 1, travels at about 17 kilometers per second relative to the Sun. The Parker Solar Probe, designed to study the Sun up close, will eventually reach about 200 kilometers per second, but only at its closest approach to the Sun, where gravity accelerates it enormously. Out in deep space, our fastest spacecraft are slower than 3i Atlas. We've never built anything that could catch it. This speed represents millions of years of momentum conservation. Whatever event ejected 3i Atlas from its home system gave it this velocity. Since then, the object has been coasting. In the near-perfect vacuum of interstellar space, there's almost nothing to slow it down. No air resistance, no friction, just the incredibly weak gravitational pulls from distant stars. Not enough to change its speed significantly over millions of years. Our Sun's gravity bent its path, but barely changed its speed. Gravity can redirect velocity, turning the object's motion from one direction to another, but conserving the total energy. 3i Atlas came in on one trajectory, curved around the Sun in a hyperbolic arc, and exited on a different trajectory. The speed changed slightly, a few kilometers per second difference between incoming and outgoing velocities, but the object remained hyperbolic, still too fast to be captured. The speed also determines how long we had to study it. Fast-moving objects pass through quickly. 3i Atlas spent only months in the inner solar system, where our best telescopes could observe it. Then it was gone, receding into the distance, getting dimmer each day as it moved further from both the Sun and Earth. The window for observation was limited by that relentless velocity, time measured in kilometers per second slipping away. Imagine trying to photograph a car driving past at 108,000 kilometers per hour. You'd have a fraction of a second to capture the image before it was gone. 3i Atlas gave us months, which seems generous, but on astronomical timescales, it's nothing. Millions of years to cross interstellar space. Only months visible to our instruments. Then millions more years heading to wherever it's going next. The velocity will decrease slowly over cosmic time. The galaxy has gravity too, not concentrated in one star, but distributed across billions of stars. This collective gravity creates a weak pull on everything, including interstellar objects. Over hundreds of millions of years, 3i Atlas will slow gradually. But this slowing is so gradual that for all practical purposes, the object will maintain roughly its current speed indefinitely. That speed carries it inexorably outward. Right now, at this very moment, 3i Atlas is racing away from us, putting thousands of kilometers between us every second. By the time you finish reading this sentence, it will be several 100,000 kilometers further away than when you started. The distance grows, the object dims, the opportunity to learn from this visitor fades. Speed defines its existence, an object defined by motion, by the fact that it's passing through rather than staying, by the velocity that makes it forever a traveler. We almost didn't see it. 3i Atlas is small, dark, and fast. It passed through our solar system with no fanfare, no bright tail, nothing dramatic to catch attention. If not for automated sky surveys running every night, if not for computer algorithms designed to detect moving objects, it would have sailed past Earth completely unnoticed. Just another invisible traveler in the endless traffic we can't see. The object's inherent dimness makes detection difficult. Brightness in astronomy is measured in magnitude, a counterintuitive scale where lower numbers mean brighter objects. The brightest stars in the sky have magnitude around 0 or negative. The dimmest stars visible to the naked eye are about magnitude 6. 3i Atlas, at its brightest, reached magnitude 18. You'd need a decent telescope just to see it as a point of light. No chance of naked eye visibility, no chance of casual discovery. Magnitude 18 means the object is roughly 4,000 times dimmer than the faintest stars you can see without help. To put this in perspective, if the Sun were magnitude 18, you couldn't see it from Earth, even with good binoculars. You'd need a telescope. 3i Atlas was visible only to serious astronomical instruments, and even then, barely. It appeared as a faint dot among millions of other faint dots, distinguishable only by its motion. That motion is what saved it from obscurity. The Atlas survey takes images of the same patch of sky multiple times per night. Computer software compares images, looking for anything that moves between exposures. Stars don't move noticeably over hours. Asteroids do. The software flags moving objects automatically. On the night 3i Atlas was discovered, the software detected a new moving dot and added it to the list of candidates for human review. Thousands of asteroids are discovered each year. Most are unremarkable, members of the asteroid belt between Mars and Jupiter. following predictable orbits. The initial detection of 3I Atlas looked like just another asteroid. Only after calculating its orbit did astronomers realize this one was different. The preliminary orbit calculations showed hyperbolic elements. The object wasn't bound to the sun, it was passing through. This is when excitement builds. Interstellar objects are rare enough that each discovery triggers intensive follow-up observations. Astronomers worldwide were alerted. Telescopes were redirected to confirm the discovery and gather more data. Every night of clear weather became crucial. Every observation refined the orbit, confirmed the interstellar nature, added details about the object's properties. But the window was closing. 3I Atlas was already outbound when discovered, already heading away from the Sun and Earth. Each day it grew slightly dimmer as distance increased. The geometry of observation mattered too. From Earth, we can only see objects when they're not too close to the sun in the sky. Too close, and sunlight overwhelms the faint, reflected light from the object. 3I Atlas was racing toward a position where it would be lost in the sun's glare before emerging on the other side, even dimmer. The size and darkness combined to make it nearly invisible. A larger object at the same distance would have been brighter, easier to detect earlier. A brighter surface would have reflected more light, making it visible for longer. But 3I Atlas was small and dark, which meant late detection and brief visibility. We caught it during a narrow window, when it was close enough to be somewhat bright, but not so close that we'd already missed it. Timing matters enormously. If 3I Atlas had passed through our solar system a few decades earlier, before automated sky surveys existed, we would have missed it completely. The surveys that found it only became operational in recent years. Before that, asteroid detection relied on humans looking at photographic plates or film, comparing images by eye. The process was slow, and many faint objects were never noticed. 3I Atlas would have been too dim for reliable detection by older methods. Consider how many interstellar visitors we've probably missed. Before 2017, before Oumuamua, we had no confirmed interstellar objects, despite thousands of years of astronomy. Were there none? Almost certainly not. Statistical models suggest interstellar objects pass through the inner solar system regularly, perhaps several per year. We simply couldn't see them. They came and went in darkness, invisible to our instruments, undetected by our searches. Even now, with better telescopes and automated surveys, we're only catching the largest or brightest interstellar visitors. Smaller objects, darker objects, objects that don't pass close to Earth. These slip by unnoticed. The galaxy could be filled with invisible traffic, rocks and ice chunks, traveling between stars. And we'd see only the few that happen to pass near Earth while we're looking in the right direction with sufficient instrumentation. 3I Atlas represents the boundary of our detection capability. Much dimmer, and we'd miss it. Much faster through our detection zone, and we'd miss it. We caught it because it happened to pass within range of our surveys during the brief era when such surveys exist and are operating. This makes the discovery feel both fortunate and slightly sad. Fortunate because we got to observe an interstellar visitor. Sad because we're aware of how much we're missing. The object is fading now, receding beyond the reach of even our largest telescopes. Soon it will be too dim to detect, lost again in the darkness. We had our chance to study this visitor, and we took it, but the chance was brief. A few months of visibility, out of a journey spanning millions of years. We witnessed a tiny fraction of its existence, enough to know it exists, enough to learn something, but not enough to answer all our questions. The darkness reclaims it, and we're left with data, measurements, and the knowledge that somewhere out there, traveling away from us at 30 kilometers per second, is a rock from another star. The path of 3I Atlas through our solar system follows a simple, elegant curve, a hyperbola, one of the fundamental shapes in mathematics and nature. The object came from interstellar space on one side of the Sun, fell inward as solar gravity pulled it, swung around the Sun at closest approach, then climbed back outward on the other side. The Atlas's entire trajectory is symmetric, balanced, governed by gravity's unchanging laws. Closest approach to the Sun occurred in late 2024, when 3I Atlas passed within roughly 300 million kilometers of our star. This sounds far, and it is. Earth orbits at 150 million kilometers, so 3I Atlas stayed well outside Earth's orbit at its closest. For comparison, Mars orbits at about 230 million kilometers. 3I Atlas came in beyond Mars, curved around the Sun, and headed back out, never penetrating the inner solar system where Mercury, Venus, and Earth reside. This distant perihelion, the closest point to the Sun, meant the object experienced relatively little solar heating. Comets that dive close to the Sun, passing inside Earth's orbit, or even inside Mercury's, are subjected to intense heat. Ice vaporizes, surfaces crack and fragment. The comet can even break apart completely. 3I Atlas avoided this violence by staying far out, receiving only gentle warmth from the distant Sun. The object crossed Earth's orbital distance twice, once on the way in, before perihelion, when it was approaching from interstellar space and falling toward the Sun, once on the way out, after perihelion, climbing away from the Sun and heading back to interstellar space. But these crossing points weren't close encounters with Earth itself. The object passed through Earth's orbital distance at times when Earth was elsewhere in its orbit, millions of kilometers away. The two paths crossed in space, but not in time. Think of it like two cars on different roads that cross at an intersection. The roads cross, but if the cars arrive at the intersection at different times, they never meet. 3I Atlas and Earth were on crossing paths, but our timing didn't align. We observed it from a distance, tracking it with telescopes, but we never came particularly close. The nearest approach to Earth was still tens of millions of kilometers, about the distance to Mars at its closest. The trajectory's orientation in space is worth considering. The solar system isn't just a flat disk, although that's how we often picture it. The planets orbit mostly in one plane, the ecliptic, but other objects can have tilted orbits. 3I Atlas approached from above the ecliptic plane, diving downward as it fell toward the Sun, then rising back up on the other side. Its path cuts through the solar system at an angle, entering from one side and exiting from another, like a needle passing through fabric. This angled approach means 3I Atlas didn't pass particularly close to any planet. Jupiter, the gravitational giant that influences so many objects in our solar system, was nowhere near the visitor's path. Saturn, Uranus, Neptune, all far from the trajectory. The object's path was determined by its incoming velocity and angle, and those happened to carry it through a relatively empty region of space, where no major planet could significantly alter its course. Had the timing been different, had 3I Atlas arrived at a different point in the planet's orbits, it might have passed near one of them. A close encounter with Jupiter could have changed its trajectory significantly, perhaps even capturing it into a solar orbit or slingshotting it away even faster. But this didn't happen. The visitor passed through unperturbed by planets, touched only by the sun's gravity, following the pure hyperbolic path that its initial conditions dictated. The symmetry of the hyperbola means the outbound leg mirrors the inbound leg. The object is now climbing away from the sun at roughly the same speed it fell inward, just in the opposite direction. It's passing back through the same distance markers it crossed on the way in. The orbit of Neptune, reached on approach, is being crossed again now on departure. The Kuiper Belt, that distant region of icy bodies beyond Neptune, is behind it. Soon it will cross the heliopause, the boundary where the sun's influence gives way to interstellar space. The geometry ensures 3I Atlas will never return. A hyperbolic trajectory is open at both ends. It comes from infinity and returns to infinity, mathematically speaking. In practical terms, it came from interstellar space and returns to interstellar space. The sun's gravity bent the path, rotated its direction, but couldn't capture it. The object remains on an escape trajectory, bound for the darkness between stars. We can calculate exactly where 3I Atlas will be years from now, decades from now, centuries from now. The trajectory is determined, barring an incredibly unlikely collision with another object, which is virtually impossible in the emptiness of space. The path is set. In 2030, it will be here. In 2050, there. In 2100, further still. Each position is predictable with precision because gravity is mathematical, and hyperbolic orbits follow equations we understand completely. But we won't be able to see it much longer. The object is already too dim for all but the largest telescopes. Soon it will fade completely from view, too far to detect even if we point our best instruments directly at it. The trajectory continues, but our ability to observe it ends. We'll know where it is, mathematically, but we won't be able to confirm it visually. The visitor returns to invisibility, carrying on its journey unseen, just as it travelled unseen for millions of years, before we happened to notice it during its brief passage through our neighbourhood. The moment 3I Atlas was confirmed as interstellar, telescopes around the world redirected to observe it. Every major observatory with the capability to see such a dim object added it to their observation schedule. Data accumulated night by night, each clear sky bringing new measurements. This wasn't just curiosity. This was a rare opportunity to study material from another star system, to compare what exists there with what we know here, to test whether planetary formation is universal, or whether each star system is unique. Spectroscopy provided the first real insights. When sunlight reflects off an object, molecules on its surface absorb specific wavelengths. These absorption lines create a fingerprint unique to different materials. Astronomers pointed spectrographs at 3I Atlas and captured its reflected light spectrum. The data showed absorption features consistent with silicate minerals, the same rocky materials that make up asteroids in our solar system. This was both expected and significant. Expected because planets should form from similar materials anywhere. Significant because it confirmed that assumption with direct evidence. The spectrum also suggested organic compounds, carbon-based molecules, likely created by radiation exposure over millions of years in interstellar space. These weren't complex organics, nothing biological, just simple carbon chains and possibly some nitrogen compounds. but their presence indicated that the chemistry of interstellar space affects traveling objects, coating them in materials that don't exist on the surface of objects protected by planetary atmospheres. Photometric observations tracked brightness changes over time. If an object is irregularly shaped and tumbling, its brightness varies as different faces point toward us. 3-Eye Atlas showed variation, confirming it's not spherical. The brightness pattern suggested a rotation period of several hours, though the data wasn't clear enough to pin down an exact number. The tumbling is probably chaotic, not a simple spin around one axis, which makes sense for an object that's been drifting through space for millions of years with nothing to stabilize its rotation. The color measurements revealed something interesting. 3-Eye Atlas is slightly redder than average asteroids in our solar system. This reddish tint is characteristic of objects in the Kuiper belt, the region beyond Neptune, where many objects have been exposed to cosmic radiation for billions of years. The radiation creates a surface layer of complex organics that appear red in reflected light. 3-Eye Atlas. Having this color suggests it came from a similar region around its home star, a distant, cold zone where ice and rock mix and radiation exposure is the main force altering surfaces. What surprised scientists was the lack of cometary activity. 2I Borisov, the second interstellar visitor, was clearly a comet with a visible tail created by vaporizing ice. Astronomers expected 3-Eye Atlas might show similar activity as it approached the Sun, but observations showed minimal or no outgassing. Either the object has very little ice, or the ice is buried under a thick crust of non-volatile material. This difference between interstellar visitors tells us that planetary systems produce diverse objects, just like our own system has both rocky asteroids and icy comets. Thermal observations attempted to measure the object's temperature and infer something about its thermal properties. Warmer objects radiate more heat. By detecting this thermal emission, astronomers can estimate how well an object retains or sheds heat, which depends on its composition and structure. But 3-Eye Atlas was too dim for detailed thermal measurements. The data was noisy, inconclusive. We know it's cold, as expected for something far from the Sun, but exact temperatures and thermal properties remain uncertain. Radar observations were attempted, but unsuccessful. Radar astronomy works by bouncing radio waves off objects and measuring the return signal. It can reveal detailed information about size, shape, and surface texture, but radar requires a strong return signal, which means the object must be relatively close and the radar must be powerful. 3-Eye Atlas never came close enough to Earth for existing radar systems to detect it reliably. The attempt was made, but the object was too distant, too small, and too dark to return a usable signal. What we learned raises as many questions as it answers. Yes, 3-Eye Atlas is compositionally similar to objects in our solar system. Yes, it follows the same physical laws, the same orbital mechanics, the same spectroscopic principles. But we don't know its exact composition. We don't know whether it came from a planetary system similar to ours or something completely different. We don't know how old it is, beyond the minimum time it's been traveling between stars. The limitations of our observations highlight how much we still can't do. We can detect interstellar visitors now, which is progress compared to a decade ago when we'd never confirmed one. We can characterize them broadly, determining if they're rocky or icy, dark or bright, active or inert. But we can't study them in detail. We can't land on them, or send a probe close enough for high-resolution imaging. We can't sample their material directly, or drill beneath the radiation-altered surface to see what's underneath. Every observation came with a time limit. As 3I Atlas receded from the Sun and Earth, it dimmed. Observations that required hours of telescope time to achieve signal-to-noise ratios barely above detection limits became impossible as the object faded. By the time the last observations were made, astronomers were pushing their instruments to the limit, extracting every photon of light from the dimmest object they could barely detect. The data is archived now. Hundreds of images, dozens of spectra, photometric measurements from multiple telescopes. This data will be analyzed and reanalyzed for years. New techniques might extract information that current methods miss. Comparisons with future interstellar visitors might reveal patterns or differences that tell us more about how common such objects are and what diversity exists among them. 3I Atlas is gone from view, but the data remains, a snapshot of a visitor from elsewhere, evidence that we live in a galaxy where matter moves between the stars. Interstellar space is not friendly to matter. It's not empty, despite what we imagine. It contains radiation, cosmic rays, particles moving at nearly light speed. It contains thin gas, mostly hydrogen, less than 1 atom per cubic centimeter, but still present. It contains dust grains, micrometeorites, tiny fragments of matter that become bullets at the velocities involved. And through this environment, 3I Atlas has been traveling for millions of years. Cosmic radiation is the constant threat. High-energy particles, mostly protons, stream through the galaxy at relativistic speeds. They come from supernova explosions, from active galactic nuclei, from mysterious sources we haven't fully identified. These particles hit everything in their path. When they strike an atom on the surface of 3I Atlas, they transfer energy, breaking chemical bonds, creating new compounds, altering the material atom by atom. This radiation exposure is why the surface of 3I Atlas is probably so dark. Pure ice starts white and reflective. Over millions of years of cosmic ray bombardment, the ice changes. Hydrogen is stripped away. Carbon compounds form, creating complex organic molecules. These organics coat the ice in a dark crust. The process is called radiation darkening, and it affects every object exposed to interstellar radiation for long periods. The darkness we observe isn't dirt or contamination. It's the scar of millions of years in the radiation bath of interstellar space. Temperature varies wildly depending on location. In interstellar space, far from any star, temperatures hover near absolute zero, around -270 degrees Celsius. Matter at these temperatures is frozen solid. Ice is hard as rock. Even gases that are normally gaseous on Earth, like nitrogen and methane, are frozen solid. But 3I Atlas didn't stay in the cold forever. It passed near our Sun, where solar radiation heated its surface. The temperature swing is enormous, from near absolute zero in interstellar space to perhaps -150 degrees Celsius at its closest to the Sun. That's still far below freezing by Earth standards, but it's a huge change, more than 100 degrees of warming. Materials expand and contract with temperature changes. This thermal cycling creates stress. Cracks form, rocks fragment. The surface of 3I Atlas likely bears the scars of thermal stress, though we can't see details at the resolution available to our telescopes. Micrometeorite impacts are another slow erosion mechanism. In interstellar space, the density of matter is incredibly low. Encounters with dust grains are rare. but over millions of years, rare events accumulate. Each impact, no matter how small, chips away atoms from the surface. The impacts are tiny, each one removing perhaps a microscopic crater worth of material. But millions of years of impacts gradually pulverize the surface, creating a layer of fine dust, a regolith of broken, powdered rock. The velocity matters here. In our solar system, objects orbit the Sun at roughly similar speeds, so relative velocities during collisions are often low, a few kilometers per second. But 3I Atlas moved through interstellar space at 30 kilometers per second. Any dust grain it encountered would have a relative velocity determined by both motions. A head-on collision could involve relative speeds of tens of kilometers per second. At such speeds, even tiny dust grains impact with enormous energy. A grain the size of a sand particle becomes a hypervelocity bullet, yet the object survives. This tells us something about its structure. It's not fragile. It's not a loose pile of rubble barely held together by weak gravity. It has cohesion, internal strength. Probably it's a solid rock or a mixture of rock and ice frozen together into a coherent mass. The impacts chip the surface but don't shatter the object. The radiation alters chemistry but doesn't destroy structure. 3I Atlas endures because it's fundamentally durable. The lack of atmosphere helps. On Earth, temperature changes cause oxidation and weathering. Water seeps into cracks, freezes, and splits rocks apart. Wind erodes surfaces. None of this happens in space. There's no air to carry oxygen, no water to freeze and expand, no wind to erode. The surface changes, but slowly, patiently, through radiation and micrometeorite impacts only. This makes space weathering a slow process compared to Earth weathering. Magnetic fields might provide some protection, though probably minimal. If 3I Atlas contains iron-rich minerals, it might have a weak magnetic field. This field could deflect some cosmic rays, reducing radiation damage slightly. But the field would be weak compared to planetary magnetic fields. Earth's magnetic field protects us from much of the solar wind and cosmic radiation. An asteroid-sized object's field, if it exists at all, provides negligible protection. 3I Atlas faces the full force of interstellar radiation. The rotation helps distribute exposure evenly. As the object tumbles, different faces point toward different directions. No single spot receives constant radiation from one direction. The bombardment is uniform over time, coating the entire surface in that dark, radiation-processed crust. If the object didn't rotate, one side might be more darkened than the other, but the tumbling ensures uniformity, a dark surface all around. Internal temperature remains constant. Heat doesn't penetrate deep into rock or ice quickly. The surface might heat up when near a star, but a meter below the surface, the temperature barely changes. The interior of 3I Atlas is probably still at the temperature of interstellar space, frozen solid, unchanged by its brief passage near our Sun. Only the outermost layer, maybe the top few centimeters, experienced warming. Below that, the cold persists, a reservoir of ancient ice that has never thawed. This durability across millions of years is almost peaceful to contemplate. The object simply exists, traveling, enduring, changing only at its surface. No catastrophic events, no dramatic destruction, just slow, steady erosion and alteration, the patient work of cosmic forces acting over timescales so long that mountains on Earth could rise and fall multiple times, while 3I Atlas travels the distance between stars. The universe is violent in places, in supernova explosions and black hole accretions. But here, in the vast empty between stars, violence is rare. There's only the slow persistence of matter, surviving, continuing, existing through ages too long for human minds to easily grasp. Three-Eye Atlas is not alone in its journey. It's the third confirmed interstellar visitor. But the story begins with Oumuamua, the object that changed everything we thought we knew about interstellar visitors and what we might find when we started looking for them. Oumuamua appeared in October 2017, detected by the Pan-STARRS telescope in Hawaii. The name means scout or messenger in Hawaiian, fitting for the first confirmed visitor from another star. Initial observations showed it was small, maybe a few hundred meters long, moving on a hyperbolic trajectory at 26 kilometers per second. But Oumuamua had features that puzzled scientists and remain debated today. The shape was unusual, highly elongated, possibly 10 times longer than it was wide. This made it unique among observed asteroids and comets, which are typically more rounded or only moderately elongated. The extreme shape suggested it might be a fragment from a larger body, broken off by some violent event. Or it might represent a type of object we simply hadn't encountered before, something common in other star systems, but absent or rare in ours. Even stranger was the acceleration. As Oumuamua moved away from the Sun, its trajectory deviated slightly from the purely gravitational path it should have followed. Something was pushing it, creating a tiny but measurable acceleration. Comets show similar acceleration when ice vaporizes and creates jets, but Oumuamua showed no sign of a tail or outgassing. The acceleration without visible cometary activity sparked speculation, some scientific and some less so, about what could cause such an effect. The most likely explanation involves invisible outgassing. Perhaps Oumuamua was a comet with a thick crust that prevented visible dust from escaping, while still allowing gas to vent. The gas would create thrust without creating a visible tail. Or perhaps it was venting unusual volatiles, materials that vaporize at different temperatures than water ice. These explanations work within known physics, though they require Oumuamua to be somewhat unusual in composition or structure. Then came 2I Borisov in August 2019, discovered by amateur astronomer Gennady Borisov. This object was refreshingly normal, at least compared to Oumuamua. It was clearly a comet with a visible tail. It outgassed like comets in our solar system do. Its composition appeared similar to solar system comets. Borisov was exactly what astronomers expected an interstellar comet to look like, which made it valuable scientifically precisely because it wasn't surprising. Spectroscopic observations of 2I Borisov's tail showed it was venting water vapor and carbon dioxide, just like our comets. The coma, the cloud of gas and dust around the nucleus, had familiar spectral features. The object was reddish, consistent with organic compounds on the surface. In almost every measurable way, Borisov could have been a comet from our Oort cloud, the distant reservoir of comets surrounding our solar system. The similarity suggested that comet formation produces comparable objects around different stars. The tail structure changed as Borisov approached, and then receded from the Sun, exactly as expected. Near the Sun, increased heat meant more outgassing and a brighter, longer tail. Moving away, the tail dimmed and shortened. The behavior followed predictable patterns, comforting in its normality. After the strangeness of Oumuamua, Borisov felt like meeting an old friend, familiar and understandable. Now, we have 3I Atlas, falling somewhere between its predecessors in terms of character. Not as bizarre as Oumuamua, with its elongated shape and unexplained acceleration. Not as overtly commentary as Borisov, with its obvious tail. More subdued, darker, quieter. If Borisov was an extroverted comet, announcing its presence with a bright tail, 3I Atlas is an introvert, passing through with minimal fuss. Each visitor teaches something different. Oumuamua taught us that interstellar objects can be strange and don't always fit our expectations. Borisov taught us that planetary formation is probably universal, creating similar objects around different stars. 3I Atlas is teaching us about the diversity within interstellar visitors, showing that not every object from elsewhere will be dramatic or easily categorized. The differences might reflect different origins. Oumuamua could be a fragment from a collision, which would explain its unusual shape. Borisov likely came from a comet cloud around another star, ejected by gravitational perturbations. 3I Atlas might be an asteroid-like object, or a comet with a very thick crust, or something in between. Each object carries clues about the processes that formed it and the system it came from, but we're still learning to read those clues. What's becoming clear is that interstellar visitors are diverse. We've seen 3, and they've all been different. This suggests the galaxy contains many types of interstellar objects, just as our solar system contains asteroids, comets, meteoroids, dust, and ice. The visitors represent a sample of this diversity, each one a messenger from systems we can't otherwise study in detail. More visitors will come. Our surveys are improving. We're getting better at detecting faint, fast-moving objects. The 4th interstellar visitor might be discovered next year, or in 5 years, or tomorrow. Each one will add to our understanding. Each one will be compared to its predecessors. Patterns might emerge, or the diversity might continue to surprise us. Either way, we're building a catalogue of visitors, a collection of samples from the wider galaxy, delivered to our doorstep by the patient processes of stellar ejection and million-year journeys through the dark. The 3 visitors we've seen represent just the beginning. Statistical estimates suggest several interstellar objects pass through the inner solar system each year. Most are too small or too dim to detect. Our current technology catches only the most visible examples. Future telescopes, more sensitive surveys, better algorithms, these will reveal more visitors. The trickle of discoveries will become a stream, then perhaps a flood. And with each new visitor, our understanding of the galaxy's wanderers will deepen. Atlas carries something precious, not gold or diamonds, though it might contain trace amounts of both. What it carries is matter from another star system, atoms that formed in a different molecular cloud, minerals that crystallized around a different sun, ice that condensed in the cold reaches of an alien planetary system. This material, mundane as it might seem, is scientifically priceless because it's from elsewhere. The atoms themselves are universal. Carbon is carbon, whether it formed here or there. Oxygen atoms are identical, regardless of which star they orbited. The periodic table is the same throughout the universe. But the way these atoms combine, the minerals they form, the isotope ratios, these can vary. Different stellar environments produce slightly different proportions of isotopes. Supernova explosions enrich nearby regions with heavy elements. The material in 3I Atlas reflects the specific history of its formation region. silicon and oxygen combine to form silicates, the rock-forming minerals that make up most rocky planets and asteroids. The silicates in 3I Atlas crystallized around another star, in conditions that might have been slightly different from our solar system's formation. The temperature gradient, the pressure, the composition of the protoplanetary disk, all these factors influence what minerals form. Studying these minerals directly would tell us about conditions in that distant system billions of years ago. Ice is probably present, buried beneath the radiation-darkened crust. Water ice is common in planetary systems, forming wherever temperatures drop below the freezing point of water. But other ices exist too. Carbon dioxide freezes into dry ice. Methane and ammonia freeze at even lower temperatures. The exact mixture of ices depends on the composition of the original material and the temperature history of the object. 3I Atlas might contain ices we could identify if we could sample beneath its surface. Organic molecules almost certainly coat the surface. These aren't biological, just carbon-based molecules created by radiation exposure over millions of years. Cosmic rays hit simple molecules like water and methane, break them apart, and the fragments recombine into more complex forms. Formaldehyde, methanol, even amino acid precursors can form through these reactions. The dark surface of 3I Atlas is probably rich in these radiation-created organics, a layer of chemistry built up over eons of exposure. Dust grains from the interstellar medium might be embedded in the surface. As 3I Atlas travelled between stars, it passed through thin clouds of gas and dust. Some of this material would have stuck to the surface, adding a veneer of truly interstellar material on top of the object's original composition. These dust grains might include pre-solar grains, particles older than our solar system that condensed around other stars and never became part of any planet. The isotope ratios are what really matter scientifically. Isotopes are versions of elements with different numbers of neutrons. Carbon-12 and carbon-13 are both carbon, but one has an extra neutron. The ratio between isotopes varies slightly depending on the nuclear processes that created them. Different stars, different supernova explosions, different regions of the galaxy all produce slightly different isotope signatures. The isotopes in 3I Atlas would reveal details about the stellar neighborhood where it formed. If we could sample 3I Atlas directly, return even a small piece to Earth for laboratory analysis, we'd learn extraordinary things. We could date the material, determining how long ago it formed. We could identify the minerals precisely, comparing them to meteorites and lunar samples we already have. We could measure isotope ratios with high precision, perhaps identifying which type of star it formed near. We could search for complex organics, understanding what chemistry occurs during million-year journeys through space. But we can't sample it. The object passed through too quickly and too far away. We don't have spacecraft fast enough to catch it, or technology to land on it while it moves at tens of kilometers per second. We can only observe from a distance, using telescopes to analyze reflected light. This gives us broad compositional information, but misses the detailed chemistry that laboratory analysis would reveal. The frustration of this missed opportunity drives space science. We know scientifically valuable samples are out there, passing through our solar system occasionally. We can detect them now, we can track them, but we can't reach them. The technology gap between detection and direct study remains enormous. It's like being able to see a treasure chest, but not having the key to open it. Future missions might change this. Concepts exist for rapid response spacecraft that could launch when an interstellar visitor is detected, accelerate to match its velocity, and rendezvous for close study or sample collection. These missions would require technology we're developing, high-power ion drives, or even nuclear propulsion to achieve the necessary speeds. The missions would be challenging and expensive, but the scientific return would justify the cost. Until then, we observe from afar. 3I Atlas carries its cargo of alien material back into interstellar space, preserving samples from its origin that we glimpsed but couldn't touch. The atoms it contains have traveled light years. They witnessed the formation of a planetary system we'll never see. They endured radiation and cold, and the vast empty. And for a brief moment, they passed close enough for us to notice, to wonder, to wish we could hold them in our hands and understand their story. The material continues its journey. The atoms don't know they're special. They're just matter, following physics, persisting. But to us, those atoms represent connection. They're proof that the galaxy mixes itself, that matter from one stellar neighborhood can visit another, that we're part of a larger system where nothing is truly isolated. 3I Atlas carries physical samples of that connection, atoms from there visiting here, making the galaxy feel smaller and more connected than the vast distances would suggest. Interstellar space is the loneliest place in existence. The distance between our Sun and the nearest star, Proxima Centauri, is 4.2 light-years. That's about 40 trillion kilometers. To cross this distance at the speed 3I Atlas travels would take roughly 40,000 years, and Proxima Centauri is the closest star. Most stars are much farther apart. The typical distance between stars in our region of the galaxy is about 5 light-years, sometimes 10, sometimes more. Light-years measure distance using the fastest thing in the universe. Light travels at 300,000 kilometers per second. In 1 year, light covers about 9.5 trillion kilometers. When we say something is 1 light-year away, we mean light takes a full year to travel that distance. Nothing goes faster than light, yet even at light speed, crossing between stars takes years. 3I Atlas moves at 30 kilometers per second, which is fast by human standards, but glacial compared to light. Its journey between stars takes not years, but millions of years. What fills this vast space? Almost nothing. Interstellar space contains an average of about 1 atom per cubic centimeter. For comparison, Earth's atmosphere at sea level contains about 10,000 atoms per cubic centimeter. The difference is incomprehensible. Interstellar space is as close to perfect vacuum as nature provides. You could travel thousands of kilometers in interstellar space and encounter only handfuls of atoms. Those atoms are mostly hydrogen, the simplest and most common element in the universe. Helium is second most common. Everything else, all the heavier elements, exists in trace amounts. This thin gas doesn't clump or flow like air. It simply exists, spread uniformly through space, so diffuse that it might as well not be there. 3I Atlas passed through this near vacuum for millions of years, encountering so little matter that the total accumulated mass would barely coat its surface in a layer 1 atom thick. The temperature in interstellar space averages about -270 degrees Celsius, only 3 degrees above absolute zero. This isn't cold in the sense of ice or winter. This is the cold of absent heat. Space doesn't conduct temperature the way matter does. There's no air to carry warmth or chill. The temperature represents the kinetic energy of the few atoms present. Atoms moving so slowly they're nearly still. Dust grains exist in interstellar space, but they're incredibly sparse. You might encounter 1 grain per cubic kilometer. These grains are tiny, smaller than particles in smoke, made of silicates or carbon compounds. They block starlight, creating the dark patches visible in some regions of the Milky Way. But encountering one during 3i Atlas's journey would be rare, a collision happening perhaps once every few thousand years. Magnetic fields thread through interstellar space, too weak to detect easily but present. These fields are millions of times weaker than Earth's magnetic field, but over the vast distances involved, they can influence charged particles, guiding cosmic rays, shaping the structure of gas clouds. 3i Atlas, electrically neutral, would be unaffected by these fields, passing through them without interaction. Cosmic rays are the only constant companions. These high-energy particles, mostly protons, moving at nearly light speed, stream through the galaxy from supernova remnants and other energetic sources. They're rare enough that you could wait years between hits from individual particles, but over millions of years they accumulate. The surface of 3i Atlas bears the marks of this radiation. Atoms displaced, molecules broken and reformed, chemistry altered by eons of exposure. The darkness is absolute. Far from any star, there's no sunlight, no reflected light from planets, nothing but the faint glow of distant stars. The Milky Way would be visible, a band of billions of stars stretching across the sky. But individual stars would appear as points of light, no different from Earth's night sky. The nearest star to 3i Atlas during its journey might have appeared slightly brighter than the others, but not dramatically so. Just another star in a sky full of stars. The silence is equally absolute. Sound requires matter to travel through, air molecules vibrating against each other. In interstellar space, there's no air, no matter dense enough to carry sound. If you could somehow survive there, you'd hear nothing. The universe would be perfectly silent, no wind, no ambient noise, just soundless void extending in every direction. This is where 3i Atlas spent most of its existence. Not the brief warm visit to our solar system, but the cold empty between stars. Millions of years of darkness, silence, near perfect vacuum, radiation as the only interaction with the wider universe. The object travelled this emptiness alone. No companion, no destination, just motion through the void, carrying its cargo of atoms from one stellar neighbourhood toward another. The loneliness of this journey is almost incomprehensible. Humans evolved in crowds, in communities, surrounded by life and sound and interaction. We can't truly imagine millions of years alone in the dark. But 3i Atlas doesn't know loneliness. It's just matter, following physics, existing. The emptiness doesn't affect it. The silence doesn't matter. It simply travels, patient and uncaring, crossing distances that dwarf anything in human experience, moving through a void so vast that the space between Earth and the Sun, which seems enormous to us, would be lost as a rounding error in the immensity of interstellar distances. How long has 3i Atlas been travelling? We can calculate this with some confidence, though the exact number depends on assumptions about where it came from. At 30 kilometers per second, crossing 1 light year takes about 10,000 years. The nearest stars are 4 light years away, which would mean a minimum journey of 40,000 years. But that assumes 3I Atlas came from the nearest star, which is unlikely. More distant origin points mean longer travel times. If the object came from 10 light-years away, the journey took 100,000 years. 20 light-years means 200,000 years. 50 light-years, which is still relatively nearby in galactic terms, means 500,000 years. These aren't precise calculations because we don't know the exact origin, but they give us the scale. The minimum is tens of thousands of years. The maximum, if it came from a more distant star, could be millions of years. Put this in human terms. 40,000 years ago, Homo sapiens was still sharing the planet with Neanderthals. Modern humans hadn't yet spread to the Americas or Australia. We lived in small groups, hunting and gathering, without agriculture or cities or writing. If 3I Atlas started its journey then, travelling from the nearest possible origin, it has been in space through all of human civilization. Through the invention of farming, the rise and fall of empires, the Industrial Revolution, spaceflight, everything, and it's still travelling. 500,000 years pushes us back before anatomically modern humans existed. Homo heidelbergensis walked the Earth, an ancestor species that would eventually give rise to both Neanderthals and Homo sapiens. The tools were primitive stone implements. Fire was controlled, but not fully understood. Language, if it existed, was simple. While our ancestors were learning to survive in Africa and Europe, 3I Atlas was already crossing the void between stars. 1,000,000 years takes us to Homo erectus, even more primitive. These early humans had smaller brains than us, simpler tools, no clear evidence of symbolic thought or art. They hunted, gathered, survived. And somewhere in the galaxy, 3I Atlas was ejected from its home system, beginning a journey that would last through the entire evolution of modern humanity. The Earth itself has changed dramatically over these timescales. Continents move slowly, a few centimeters per year, but over hundreds of thousands of years, this adds up. The Atlantic Ocean is wider now than when 3I Atlas might have started traveling. Mountain ranges have grown measurably. Rivers have changed course. Ice ages have come and gone, covering vast regions in glaciers that later melted. The planet's surface, which seems permanent to us, has been reshaped while this rock crossed space. Climate cycles on Earth operate on timescales of tens of thousands of years. Ice ages recur roughly every 100,000 years, driven by variations in Earth's orbit. If 3I Atlas has been travelling for 500,000 years, it has been in space through 5 ice ages on Earth. Through periods when sea levels were 100 meters lower than today, because water was locked in ice sheets. Through warm periods when the climate was similar to now. The object's journey spans multiple cycles of Earth's climate system. Species have evolved and gone extinct during 3I Atlas's travel. The woolly mammoth, extinct now, was alive and thriving when this object might have begun its journey. So were countless other species that no longer exist. Evolution operates on these timescales, slowly but relentlessly changing the forms life takes. 3I Atlas has been traveling long enough for natural selection to create and destroy entire species here on Earth. Stars move too, though slowly. The constellations we see in the night sky would look slightly different if viewed 500,000 years ago. Stars have shifted position, not much, but enough to distort familiar patterns. Orion wouldn't quite be Orion. The Big Dipper wouldn't quite be the same shape. The sky itself changes over the timescales of interstellar journeys. The object has no awareness of time passing. It doesn't age in any meaningful sense. Rock doesn't grow old, The radiation damage to its surface is cumulative, yes, but there's no internal clock counting years. 3i Atlas in year 1 of its journey was essentially the same as 3i Atlas in year 100,000. No deterioration except surface changes, no wearing out, just existence, unchanged, patient. This patience is what makes interstellar travel possible for objects like this. They don't need life support. They don't need fuel. They don't run out of resources. They simply persist, following the momentum they were given at ejection, coasting through the void. Time doesn't matter, because there's nothing about the object that depends on time. It could travel for 1 million years, or 10 million, and arrive essentially unchanged. Compare this to human space travel. Our spacecraft are limited by fuel, by life support systems that break down, by human lifespans. The furthest we've sent humans is the Moon, a journey of days. Our robotic probes reach the outer solar system, journeys of years or decades. But millions of years. Impossible for anything we build. Our machines don't last that long. We barely understand how to make structures that could endure even thousands of years in space, let alone millions. Yet nature does this routinely. Objects are ejected from planetary systems, travel between stars for millions of years, and arrive intact. No maintenance, no repairs, no mission control, just rock and ice, traveling, enduring. 3i Atlas proves this is possible. That matter can survive interstellar journeys, lasting longer than human civilization has existed. The journey will continue. However long 3i Atlas has been traveling, it's not done. It passed through our solar system and is now heading back into interstellar space. Another 1 million years might pass before it encounters another star, or 10 million, or never if its trajectory never happens to intersect another stellar system. The journey that brought it here is only part of a longer journey that might never end. Motion through space that could persist until the stars themselves burn out. Somewhere in the galaxy is a star that doesn't know it sent us a visitor. We can point vaguely in the direction 3i Atlas came from, toward the constellation Ursa Major, but we can't identify the specific star. There are hundreds of possibilities in that region of sky, each one a candidate origin point. The star could be yellow, like our sun, or red, or orange. It could be slightly larger or smaller, hotter or cooler. We know almost nothing about it, except that it probably has, or had, a planetary system. Planetary systems form from disks of gas and dust around young stars. Gravity pulls material together into clumps. Small clumps merge into larger ones. Eventually, you get planets, asteroids, comets, all the debris of planet formation. This process is universal, happening around most stars, but the details vary. Each system is unique in the sizes and orbits of its planets, the amount of leftover material, the specific composition of rocks and ice that formed. 3i Atlas was probably part of this formation process. Perhaps it formed in the outer reaches of its system, in a region analogous to our Kuiper belt, where ice and rock mix in the cold beyond the major planets. Or perhaps it formed closer in and was later scattered outward by gravitational interactions. Its composition, dark and possibly icy beneath the surface, suggests a cold origin, somewhere water could freeze and remain frozen. Young planetary systems are violent places. Planets don't form in neat, stable orbits immediately. They migrate, moving inward or outward as they interact gravitationally with the disk of material around the star. These migrations cause chaos. Small objects get flung around like pinballs. Some crash into planets, adding to their mass. Some fall into the star. Some get ejected entirely, thrown out of the system at high speed. Gas giants are particularly effective at ejection. A planet like Jupiter has enormous gravity. Small objects passing near it can be accelerated dramatically, gaining enough speed to escape the star's gravity completely. Our Jupiter has probably ejected countless objects over the solar system's history. Comets that ventured too close, asteroids perturbed into unstable orbits. Anything that passed near Jupiter with the wrong trajectory could be flung into interstellar space. 3I Atlas's home system probably had at least one gas giant. This giant planet, through a close gravitational encounter, accelerated 3I Atlas to escape velocity. The encounter might have been sudden, the object swinging around the planet in hours or days, gaining speed through the slingshot effect. Or it might have been a series of encounters over millions of years, each one adding a bit more velocity until finally the accumulated speed was enough to escape. The ejection was probably billions of years ago. Planetary systems settle down after their first few 100 million years. The violent migration phase ends. Orbits stabilize. Ejections become rare. 3I Atlas was likely ejected during this early chaotic period, when its home system was still young and unsettled. This means it left a very different system than exists there now. The planets have since moved to their final positions. The leftover debris has been cleared. The system has matured while 3I Atlas has been traveling. That star is still burning. Unless it was unusually massive and has since exploded as a supernova, which is unlikely, the star continues to shine. Planets still orbit it. The system persists, older now, calmer, unaware that one of its children left billions of years ago and has just visited another star system light years away. Does the system have life? We have no way to know. If the star is sun-like and has rocky planets in the habitable zone, life is possible. But possible doesn't mean likely, and even if life exists there, it probably hasn't reached the technological level to detect 3I Atlas's visit here. The distances are too great. The object is too small. Even if that civilization has advanced telescopes, 3I Atlas would be invisible to them at interstellar distances. The star itself might be observable from Earth with large telescopes, but we don't know which star to look for. We can't trace the trajectory back with sufficient precision to identify a specific candidate. The star might be catalogued, might have been observed and measured, might even have known exoplanets, but we can't connect it to 3I Atlas. The link between object and origin is lost to time and distance. Every star probably sends visitors into the galaxy. Our Sun certainly has. Objects from our Oort cloud, the distant reservoir of comets, are occasionally perturbed into the inner solar system. Some of these pass close to planets and get ejected. Right now, former members of our solar system are traveling through interstellar space, carrying matter from our planetary system to other stars. We're contributing to the same galactic exchange that brought us 3I Atlas. This exchange has been happening since stars first formed. For billions of years, stellar systems have been leaking matter into interstellar space. The galaxy slowly mixes, material from one system eventually visiting others. Most of these visitors go unnoticed, too small or too distant to detect. But they exist, a constant traffic of rocks and ice crossing between the stars, connecting stellar systems in ways we're just beginning to recognize. The star that ejected 3I Atlas probably ejected thousands or millions of other objects too. Some might have fallen into other stars. Some might have been captured by other planetary systems, becoming permanent members of their new homes. Some might still be traveling, like 3I Atlas, on journeys that will last millions more years before encountering another star. That unknown star, somewhere in Ursa Major, has given us a gift, whether it knows it or not. It sent us a sample of its planetary system, a piece of matter that formed in its protoplanetary disk billions of years ago. This gift crossed light years of empty space to reach us. We glimpsed it briefly, learned what we could, and now watch it leave. The connection between our star and that star is temporary, mediated by this small rock, but it's real. We touched, however indirectly, a solar system we'll never visit. Atlas is not alone. Right now, at this moment, other interstellar objects are passing through our solar system. We can't see most of them. They're too small, too dark, too far from optimal viewing positions. But statistical models tell us they're there. The galaxy is filled with these wanderers, rocks and ice chunks traveling between stars. A vast invisible traffic we're only beginning to detect. Estimates vary, but most astronomers think several interstellar objects pass through the inner solar system each year. Some models suggest even more, perhaps dozens or hundreds. These numbers come from scaling up our detections. We've found 3 in several years of searching. Our searches only catch the brightest, largest, or closest objects. Most pass by unseen. If we can detect a few, there must be many more we're missing. The total population of interstellar objects in the galaxy is staggering. Every star probably ejects millions or billions of objects over its lifetime. With hundreds of billions of stars in the Milky Way, the number of interstellar wanderers could exceed the number of stars themselves. The galaxy might contain more interstellar objects than solar system-bound objects, more travelers than residents. These objects exist at all scales. Some are small, boulder-sized or smaller, too tiny to detect, even if they passed near Earth. Some are larger, like 3I Atlas, a few hundred meters across. Some might be much larger, kilometers in diameter, planetoids wandering between stars. The size distribution probably mirrors what we see in asteroid belts and comet clouds. Lots of small objects, fewer large ones, with the total mass concentrated in the biggest examples. They're moving in every direction. Some are heading toward the galactic center, some toward the outer edges, some moving perpendicular to the galactic plane, each one following the trajectory it was given at ejection, modified slightly by gravitational interactions with stars it passed near. The velocities vary too. Some move slowly, relatively speaking, at 10 or 15 kilometers per second. Others move much faster, 50 or 100 kilometers per second or more. Speed depends on the violence of the ejection event. The invisible traffic crosses itself constantly. Interstellar objects pass near each other in the emptiness, usually too far apart to interact gravitationally, but occasionally close enough for a near miss. Very rarely, 2 objects might actually collide, a catastrophic impact at tens of kilometers per second that shatters both objects into thousands of fragments. These collision fragments become new interstellar objects, smaller pieces continuing the journey their parents started. Our solar system sits in a stream of this traffic. Objects are constantly entering our gravitational sphere of influence, being deflected slightly by the sun and exiting. Most of these encounters happen far out, beyond Neptune, in the empty reaches where our sun's gravity is weak. the objects curve slightly and continue on their way, barely aware they passed through a stellar system. Some come closer. A few, like 3i Atlas, pass through the inner solar system, where our telescopes can detect them. These close passages are rare, but not vanishingly rare. On average, we should expect one detectable interstellar visitor every year or two. Our current detection rate matches this prediction, suggesting our models are roughly correct. As our surveys improve, we'll find more, confirming or refining the estimates. The galaxy has been doing this for billions of years. Since the first stars formed planets, those planets have been ejecting debris. The early galaxy must have been even more chaotic. Young stellar systems violently throwing out material. By now, trillions upon trillions of objects have been ejected. Most are still traveling. Some have fallen into other stars or been captured by planetary systems. But the majority are still out there, crossing the dark between stars. This creates a kind of galactic ecosystem. Matter doesn't stay locked in individual stellar systems. It circulates slowly on timescales of millions or billions of years. An object ejected from one star might eventually be captured by another, becoming part of that new system. The atoms in that object, originally from the first star's protoplanetary disk, are now part of a second stellar family. The galaxy mixes itself through this slow exchange. Some of these wanderers might be older than the Sun. Our solar system formed 4.6 billion years ago from a cloud of gas and dust that itself came from previous generations of stars. That cloud might have contained interstellar objects, rocks already traveling between stars when our Sun was born. These ancient wanderers could have been incorporated into our solar system, becoming asteroids or comets indistinguishable from objects that formed here. The realization changes how we think about planetary systems. We're not isolated. We're not separate islands in space. We're part of a connected network where matter flows between systems over cosmic timescales. Our solar system has given material to the galaxy and received material in return. We're participants in a galactic exchange that's been ongoing since stars first formed planets. This connectivity feels profound. It means we're related to other stellar systems, not just through shared physics or chemistry, but through actual physical exchange of matter. The atoms in 3i Atlas came from another system. Atoms from our system are traveling elsewhere. We're connected through this material flow, linked in ways that transcend the vast distances between stars. Future astronomy will map this traffic in detail. Better surveys will detect more interstellar objects. We'll build catalogues of their properties, tracking their trajectories, understanding their compositions. We might discover patterns, preferred pathways through the galaxy, regions where interstellar traffic is denser. We might find objects that have visited multiple star systems, traveling from one to another in a cosmic journey spanning the galaxy's lifetime. The galaxy is more dynamic than we thought. It's not static, with matter locked forever in individual solar systems. It's flowing, mixing, circulating. Objects travel between stars constantly, creating connections, exchanging material, making the galaxy feel smaller and more integrated. And we're part of this. We live in a system that both sends and receives these visitors. We're nodes in a vast network of matter exchange that encompasses the entire galaxy, a network operating on timescales so long that human civilization is invisible to it, but operating nonetheless, patient and persistent, connecting stars through the simple mechanism of rocks traveling through space. Where is 3I Atlas going? We can trace its trajectory into the future with mathematical precision. The path is determined, set by its current velocity and the gravity of stars it will pass near. In 100 years, it will be here. In 1,000 years, there. In 10,000 years, somewhere else. We can predict its position centuries or millennia from now, because orbital mechanics is exact and the forces acting on it are understood. But will it ever encounter another star? This is harder to answer. Space is vast, and stars are far apart. The galaxy contains hundreds of billions of stars, but even with so many stars, the space between them is mostly empty. An object traveling in a straight line through the galaxy might pass near stars occasionally, or it might travel through empty regions for billions of years without coming particularly close to anything. The probability of close encounter depends on trajectory and time. Over millions of years, the odds favour eventually passing near another star. Over billions of years, multiple encounters become likely. But these are statistical predictions, not certainties. 3I Atlas might pass within a few light years of a star in 1,000,000 years, close enough for that star's gravity to deflect it significantly. Or it might travel 10 million years before such an encounter, or longer. The galaxy is random in this way, with matter distributed unevenly and trajectories following paths that sometimes intersect stellar systems and sometimes don't. Even a close encounter doesn't guarantee capture. For 3I Atlas to be captured by another star, it would need to lose velocity through some mechanism. In our solar system, it retained its hyperbolic trajectory because nothing slowed it down enough. The same will likely happen at the next star it approaches. It will curve around the star, perhaps pass through that system's inner regions, and exit on a new trajectory, still moving at interstellar speeds. But planetary interactions could change this. If 3I Atlas happens to pass very close to a gas giant at the right angle, the planet's gravity could slow it down enough to trap it. The object would become a comet or asteroid in that new system, a permanent capture. This is rare but possible. Some objects in our own solar system might be captured interstellar visitors, indistinguishable from native objects, except for subtle differences in composition or orbit that we haven't detected yet. More likely, 3I Atlas will remain a wanderer. It will pass near stars, be deflected, change direction, but keep moving. The galaxy's collective gravity will slow it slightly over hundreds of millions of years, but not enough to stop it. The object will travel indefinitely, a permanent citizen of interstellar space, rather than any particular stellar system. Over billions of years, the trajectory becomes unpredictable. Small gravitational perturbations compound. An encounter with one star changes the path slightly. The new path leads to a different region of the galaxy where different encounters occur. These encounters change the path again. After billions of years and thousands of stellar encounters, the trajectory has wandered far from what we can predict now. The object might end up anywhere in the galaxy. Eventually, on truly cosmic timescales, 3I Atlas will meet one of a few possible fates. It might be captured by a star, ending its interstellar wandering. It might collide with another object, a planet or asteroid, or another interstellar wanderer, being destroyed in the impact. It might fall into a star, vaporizing in the stellar atmosphere. Or it might simply continue traveling until the galaxy itself changes. Galaxies aren't permanent. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. The collision won't be direct. Stars won't crash into each other because stars are so far apart. But the two galaxies will merge, their structures intermingling, their stars and gas mixing. During this merger, gravitational chaos will fling many objects into intergalactic space. 3I Atlas might be one of them, ejected not from a star but from a galaxy, becoming an intergalactic wanderer, traveling between galaxies rather than between stars. In the deep future, trillions of years from now, the universe itself will have changed. Stars will have burned out, the last of them fading to darkness. Galaxies will have merged or been separated by cosmic expansion. The universe will be cold, dark, and empty in ways we can barely imagine. And 3I Atlas, if it survives that long, will still be traveling. It will move through a dead galaxy, past stellar remnants and black holes, the only light coming from occasional flares of matter falling into black holes. The rock will persist, unchanged, traveling through a universe that no longer resembles the one it formed in. This eventual fate seems lonely from a human perspective. We're creatures of change, of life cycles, of beginnings and endings. The idea of endless wandering, with no destination and no conclusion, feels pointless to us. But 3I Atlas doesn't have perspective. It doesn't experience loneliness or purpose. It simply exists, following physics, persisting. The journey isn't lonely to the object, because loneliness requires awareness. There's something peaceful in this persistence. The object asks nothing of the universe. It expects nothing. It simply travels, patient and eternal, moving through whatever space it finds itself in. Stars might be born and die during its journey. Galaxies might collide. The universe might expand into eventual heat death. And through all of this, 3I Atlas continues, a tiny piece of matter following the momentum it was given billions of years ago, unaware of the cosmic changes around it, existing without meaning or purpose, just existing. Right now, the object is heading away from us, putting millions of kilometers between us every day. The distance grows, the connection fades. Soon we won't be able to detect it, even with our largest telescopes. It will return to invisibility, to the darkness it knew, before passing through our small corner of the galaxy. And it will continue, on and on, through time periods we can calculate but not truly comprehend. Traveling toward a future we can predict statistically, but not know specifically. A wanderer without home, without destination, without end. The existence of 3I Atlas tells us something fundamental about how planetary systems form. They're messy, they're chaotic. They don't assemble neatly from a disk of material into stable planets, and then stop. The process involves violence, ejections, collisions, migrations. Every planetary system probably goes through a phase where it throws out enormous amounts of material, including objects like 3I Atlas. Planet formation begins with a protoplanetary disk, a flat cloud of gas and dust orbiting a young star. Gravity pulls material together. Dust grains stick to each other, forming larger clumps. Clumps collide and merge, growing from pebbles to boulders to mountains to planetesimals, objects hundreds of kilometers across. Eventually, planetesimals collide to form planets. This is the basic story, but the details are violent and chaotic. Not everything becomes a planet. Most of the material in the disk doesn't merge into large bodies. Some remains as asteroids, too small to grow further. Some becomes comets in distant orbits. And some gets ejected entirely, flung out of the system by gravitational interactions with the growing planets. 3I Atlas represents this ejected category, the leftovers that didn't make it into planets and didn't stay in stable orbits. The ejection happens through close encounters with massive planets. Jupiter-sized worlds have gravity strong enough to accelerate small objects to escape velocity. A planetesimal passing near such a planet gains speed through gravitational slingshot. If it gains enough speed, it escapes the star's gravity entirely. This process cleared much of the debris from our early solar system. Jupiter and Saturn, acting as gravitational vacuum cleaners, ejected countless objects that once orbited our Sun. Our solar system probably ejected as many objects as remain in it now. The asteroid belt, the Kuiper belt, the Oort cloud, all together contain billions of objects. But an equal or greater number were ejected during the solar system's formation and early evolution. These ejected objects are now interstellar wanderers, traveling between stars, some of them perhaps visiting other planetary systems, the way 3I Atlas is visiting ours. This means planetary formation is a galaxy-wide process, not limited to individual stellar systems. Yes, planets form around stars, but the process also creates interstellar objects. These objects carry material from one system to another, mixing the galaxy slowly over billions of years. The atoms in planets around distant stars might include material ejected from our solar system. The atoms in our asteroids might include material from other stars. The violence of early planetary systems creates a specific size distribution of ejecta. Small objects are common. Large objects are rare. This is because small objects are easier to accelerate to high speeds. A boulder-sized chunk can be flung to escape velocity more easily than a mountain-sized chunk. The energy required increases with mass, so the bigger the object, the less likely it is to be ejected. 3I Atlas, at a few hundred meters across, represents a moderately large example. Larger interstellar objects exist but are rarer. The composition of interstellar objects reflects the composition of their source region. 3I Atlas, dark and possibly icy beneath its radiation-processed crust, likely came from the outer reaches of its home system. Objects from inner regions would be more rocky, less icy. The variety we see among the three detected interstellar visitors suggests they come from different parts of different systems, sampling the diversity of planetary formation outcomes. Young stellar systems are more violent than old ones. In the first few 100 million years, planets are still migrating, orbits are still unstable, collisions are common. This early phase produces most ejections. By the time a system is 1 billion years old, it has settled. Ejections become rare. Most of the debris has been cleared into stable orbits or ejected entirely. 3I Atlas was probably ejected during this violent youth, billions of years ago, when its home system was still chaotic. Every star with planets probably has ejected material. Stars without planets might eject less, having less gravitational chaos to accelerate objects. But any star with a planetary disk goes through the formation process and the associated ejections. This makes interstellar objects common, a natural byproduct of planet formation, rather than a rare exception. The universality of this process means we can learn about planetary systems we can't observe directly by studying interstellar visitors. We can't send probes to other stars with current technology. We can't study their asteroids and comets except through distant telescope observations. But when those systems send us samples through ejection, we can study those samples up close, learning about conditions and composition in regions we can't otherwise access. 3I Atlas and its fellow travelers are ambassadors from distant planetary systems. They're not intentional emissaries, they're just rocks following physics. But they carry information about where they came from, encoded in their composition and structure. Each visitor is a data point about planetary formation elsewhere, a piece of evidence that planet formation is universal and produces similar outcomes around different stars. The chaos that created 3I Atlas created us too. The same violent processes that ejected interstellar wanderers also built planets. Jupiter's gravity helped eject objects like 3I Atlas, but Jupiter's gravity also protected Earth from bombardment, allowing life to develop. The violence and the stability are linked, two outcomes of the same process. We exist because planetary formation is violent enough to clear debris, but controlled enough to create stable worlds. Understanding this process helps us understand our own solar system's history. We look at 3I Atlas and see evidence of processes that happened here too. The ejections, the gravitational chaos, the leftovers wandering between stars. All of this happened around our sun. We're learning our history by studying visitors from elsewhere, recognizing our past in the debris of other systems. The galaxy teaches us about ourselves through the wanderers it sends our way. The discovery of interstellar visitors is accelerating. We found the first in 2017, the second in 2019, the third in 2024. The intervals between discoveries are shrinking as our detection capabilities improve. More sensitive telescopes, better algorithms, automated surveys that never sleep. All of these advances make finding interstellar objects easier. The future will bring more discoveries, many more, until detecting interstellar visitors becomes routine rather than exceptional. The Vera Rubin Observatory, scheduled to begin operations soon, will transform interstellar object detection. This telescope will survey the entire visible sky every few nights, imaging vast areas with a single exposure. Its camera is the largest ever built for astronomy, 3,200 megapixels, capable of detecting incredibly faint objects. Computer algorithms will process the images automatically, flagging anything that moves between exposures. The system is designed to find asteroids and comets in our solar system, but it will find interstellar visitors too. Estimates suggest Vera Rubin might detect several interstellar objects per year, possibly dozens. This would transform our understanding from 3 examples to hundreds within a decade. With larger samples come better statistics. We'd learn the size distribution, the composition range, the diversity of trajectories. We'd start to recognize patterns and classify interstellar visitors into types, just as we classify asteroids and comets in our own system. Space-based telescopes will help too. The James Webb Space Telescope and future infrared observatories can detect the thermal emission from interstellar objects, measuring their temperature and inferring properties that optical telescopes miss. These observations work best for objects that have recently passed near the sun and are still warm. The thermal glow reveals information about composition and structure that reflected light alone cannot provide. Rapid response systems are being developed. When an interstellar object is detected, astronomers worldwide receive alerts within hours. Telescopes are redirected to observe the new visitor as quickly as possible. Every night of observation matters because these objects are only visible for months before they fade beyond detection. The faster we respond, the more data we collect, the better we understand each visitor. Some groups are designing spacecraft missions to intercept interstellar visitors. The challenge is enormous. These objects move fast and give little warning before passing through. A spacecraft would need to launch quickly after detection, accelerate to match the object's velocity, and rendezvous for close study. Current rocket technology can't achieve this easily, but future propulsion systems might. Nuclear thermal rockets or ion drives with high power could make such missions feasible. One proposed mission concept involves a spacecraft on standby, already in space, waiting for an interstellar visitor to be detected. Once a suitable target is identified, the spacecraft activates, accelerates toward an intercept trajectory, and catches up with the object. The spacecraft would fly alongside the visitor for weeks or months, imaging it at close range, measuring its composition with onboard instruments, perhaps even landing to collect samples. Sample return is the ultimate goal. Bringing material from an interstellar object back to Earth would revolutionize what we can learn. Laboratory analysis is far more detailed than anything telescopes can provide. We could measure isotope ratios precisely, identifying the stellar environment where the material formed. We could search for complex organic molecules, understanding the chemistry of interstellar space. We could date the material, determining when the object formed and how long it's been traveling. Such a mission might launch in the 2030s or 2040s if technology and funding align. The target would be chosen from objects detected by surveys like Vera Rubin, selected for favorable trajectory and composition. The spacecraft would chase the object, catch up, collect samples, and return them to Earth over 8 Equisci mission, lasting perhaps a decade or more. The samples would be studied for generations, revealing secrets about planetary formation elsewhere in the galaxy. Ground-based radar could improve detection and characterization. Powerful radar systems can bounce signals off objects and measure the return, revealing size, shape, and surface texture. Current radars have limited range, but next-generation systems might detect interstellar visitors at greater distances. Radar provides information that optical telescopes cannot, complementing visible light observations with detailed structural data. Amateur astronomers will contribute too. Citizen science projects already help discover asteroids and comets. The same approach works for interstellar visitors. Volunteers examine images, flagging unusual objects for professional follow-up. With millions of images generated by surveys like Vera Rubin, human pattern recognition can supplement automated algorithms, catching objects the software might miss. International cooperation is essential. Interstellar objects don't respect borders. They're discoveries for all humanity, regardless of which country's telescope first detects them. Data sharing between observatories, coordinated observation campaigns, collaborative research, all of this maximizes what we learn from each visitor. The objects are rare enough that every detection matters, making cooperation more valuable than competition. The future might bring surprises. We've seen 3 interstellar visitors, and they've all been different. Future discoveries might reveal even more diversity. We might find metallic objects, pure iron-nickel asteroids from the cores of shattered planets. We might find objects with unusual compositions, materials rare in our solar system, but common elsewhere. We might even find something completely unexpected, something that challenges our understanding of what interstellar objects can be. Each discovery teaches us. Each visitor adds data to our understanding of the galaxy's invisible traffic. Within a few decades, we'll transition from surprise at finding interstellar objects to cataloguing them routinely. Astronomers will specialize in interstellar visitor science. Databases will track hundreds or thousands of confirmed visitors. Patterns will emerge showing us how common these objects are, where they come from, what they're made of, how they move through the galaxy. The era of interstellar visitor astronomy has just begun. We're at the start of a journey that will reveal the galaxy's network of wandering objects, connect stellar systems through material exchange, and teach us about planetary formation across light years of space. 3i Atlas is part of this beginning, one early chapter in a story that will unfold for centuries as we discover more visitors and learn to read the messages they carry. Could life hitchhike between stars on objects like 3i Atlas? This question is serious science, not science fiction. The theory is called panspermia, the idea that life, or at least the building blocks of life, might spread between planetary systems on rocks traveling through space. If true, life on Earth might have originated elsewhere, delivered here on an interstellar visitor billions of years ago. The conditions during the journey are brutal. Interstellar space is cold, near absolute zero. It's bathed in cosmic radiation that breaks apart complex molecules. There's no water, no air, no protection from high-energy particles. Any organism exposed to these conditions would die quickly. But microbes are surprisingly hardy. Some can survive in extreme environments, frozen for millennia, subjected to radiation doses that would kill humans instantly. Certain bacteria form spores when conditions become unfavorable. Spores are dormant, metabolically inactive, incredibly resistant to damage. They can survive freezing, desiccation, radiation, vacuum, all the conditions of space. Laboratory experiments have exposed bacterial spores to space-like conditions and found that some survive. Not all, not even most, but some fraction remains viable even after years of exposure. The key is protection. Microbes on the surface of an interstellar object would die from radiation, but microbes buried inside, protected by meters of rock or ice, might survive. The rock shields them from cosmic rays. The cold preserves them, preventing decay. Deep inside a large enough object, conditions aren't pleasant, but they're survivable for organisms in dormant states. 3i Atlas might carry microbes inside it right now. If its home system had life, and if some of that life ended up on the object before ejection, and if those organisms survived the journey, then this rock passing through our solar system could contain alien microbes. They would be dormant, frozen, waiting for conditions to improve. If 3i Atlas were ever captured by a planet with liquid water and suitable chemistry, those microbes might revive. Earth might have been seeded this way. In its early history, 4 billion years ago, Earth was bombarded by asteroids and comets. Some of these might have been interstellar visitors, carrying microbes from other worlds. If those microbes found suitable conditions on early Earth, they could have begun reproducing, eventually evolving into the diversity of life we see today. We might all be descendants of interstellar travelers. Testing this theory is difficult. We'd need to sample an interstellar object directly, drill into its interior, and search for life or signs of past life. This requires a spacecraft mission that hasn't been attempted yet. Even if we found organic molecules, complex carbon compounds, that might be biological in origin, we couldn't be certain they came from life, rather than from non-biological chemistry. The probability of panspermia depends on many unknowns. How common is life in the galaxy? If life is rare, the chance of an interstellar object carrying it is small. If life is common, many objects might carry dormant microbes. How often do living planets eject material into space? Asteroid impacts can blast rocks off planets. Some of these rocks might escape the planetary system entirely, carrying microbes with them into interstellar space. Mars might have sent life to Earth this way. Early Mars had liquid water and might have developed life before Earth did. Impacts on Mars have definitely ejected material, some of which has landed on Earth as meteorites. If early Mars had microbes, some might have survived the journey to Earth, seeding our planet with Martian life. This is a specific version of panspermia called lithopanspermia, life spreading via rocks. The timescales work. Objects like 3I Atlas travel for millions of years, but bacterial spores can survive that long if protected. The journey is slow, but dormancy is patient. A microbe doesn't care if the journey takes 1,000,000 years because it's not experiencing time in any meaningful way. It's frozen, waiting, preserved by the very conditions that would kill an active organism. If panspermia happens, it makes the galaxy's biosphere more connected than we imagine. Life wouldn't be limited to individual planets. It would spread between systems, creating a galactic ecosystem where organisms from one world occasionally seed others. This doesn't mean advanced life spreads easily. Complex organisms wouldn't survive the journey. But simple microbes might, and simple microbes can evolve into complexity given the right conditions. Earth's life might be related to life on distant planets through this mechanism. We might share common ancestors with organisms light years away, separated not just by space, but by billions of years of independent evolution. The differences would be enormous after so much time, but the underlying chemistry might show similarities that reveal the shared origin. However, panspermia doesn't solve the origin of life. It just moves the question: if life on Earth came from elsewhere, how did life originate there? At some point, in some location, life had to arise from non-living chemistry. Panspermia could spread life after it originated, but it can't create life in the first place. The fundamental question of abiogenesis, how life begins, remains unanswered, regardless of whether life spread between stars. Scientists take panspermia seriously enough to design experiments and missions around it. Sample return missions from interstellar objects would search for biosignatures, chemical or physical evidence of life. Finding such evidence would be extraordinary, proof that life exists elsewhere and travels between stars. Even finding complex organics that aren't clearly biological would be significant, showing that the chemistry of life occurs in interstellar objects. The ethical questions are complex too. If we found living microbes on an interstellar object, what should we do? Bringing them to Earth could be dangerous if they're harmful to terrestrial life. Quarantine protocols would be essential, but studying them could teach us enormous amounts about biology, showing us whether life elsewhere uses the same chemistry and mechanisms as Earth life, or something completely different. For now, we don't know if panspermia happens. We know it's possible in principle. We know microbes can survive relevant conditions in laboratories, but we don't know if the galaxy actually works this way. 3i Atlas might carry dormant life, or it might be sterile. Until we can sample such objects directly, the question remains open, hanging in the peaceful uncertainty of what might be traveling through space on these ancient rocks. We've sent our own visitors into the galaxy. 2 spacecraft, Voyager 1 and Voyager 2, launched in 1977 to study the outer planets. They completed that mission decades ago, flying past Jupiter, Saturn, Uranus, and Neptune, sending back images and data that transformed our understanding of these worlds. But they didn't stop. They kept going, powered by momentum and nuclear batteries, heading out of the solar system into interstellar space. Voyager 1 crossed the heliopause in 2012, the boundary where the solar wind gives way to the interstellar medium. This made it the first human-made object to enter interstellar space. Voyager 2 followed in 2018, crossing at a different location and providing complementary data about the boundary region. Both spacecraft are now traveling through interstellar space, becoming wanderers like 3i Atlas, though much smaller and carrying very different cargo. The spacecraft are moving at about 17 kilometers per second relative to the Sun, slower than 3i Atlas, but still fast enough to escape the solar system permanently. They'll never return. They'll coast through interstellar space for millions or billions of years, long after their power sources die and their instruments fall silent. They're Earth's contribution to the galaxy's traffic of wandering objects. Each Voyager carries a golden record, a phonograph disc encoded with sounds and images from Earth. The records include greetings in 55 languages, music from various cultures, natural sounds like thunder and birdsong, and images showing human life and the diversity of Earth. The records are meant for any intelligence that might find the spacecraft in the distant future. A message in a bottle thrown into the cosmic ocean. The golden records include instructions for playing them, assuming the finder has basic knowledge of physics and mathematics. The playback speed is indicated using hydrogen atom transitions, a universal constant that any technological species should recognize. The images are encoded as analog signals, requiring technology to reconstruct them. But the encoding is explained through diagrams on the record's cover. Will anyone ever find them? The probability is incredibly small, but not zero. The spacecraft will pass near other stars eventually, though near means light years of distance. In all, about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. That's closer than Proxima Centauri is to us now, but still too far for easy detection, unless someone is specifically looking for small objects in interstellar space with very sensitive instruments. In 300,000 years, Voyager 2 will pass within a similar distance of Sirius. The spacecraft will continue on such trajectories indefinitely, occasionally passing near stars, but mostly traveling through empty space. The nuclear power sources will have long since failed. The spacecraft will be cold, dark, inert, but the golden records will remain intact, protected by their covers, waiting for a discovery that might never come. These spacecraft are our equivalent of 3i Atlas, small objects ejected from a planetary system on trajectories that will carry them between stars. The difference is intention. 3i Atlas was ejected by natural processes, gravity, and orbital chaos. Voyagers were launched deliberately, built by a civilization that wanted to explore and communicate across the cosmos. But the end result is similar Objects traveling through interstellar space, carrying samples from their origin system. The Voyagers are fragile compared to natural interstellar objects. They're made of aluminum, electronics, instruments, materials that will slowly degrade over millions of years from radiation and micrometeorite impacts. But the basic structure should last for an incredibly long time. The gold records are particularly durable, gold being resistant to corrosion and radiation damage. Long after the spacecraft framework has eroded, the records might survive, thin disks of gold floating through space. Future civilizations on Earth might send more interstellar probes. Plans exist for missions using advanced propulsion to reach nearby stars within human lifetimes. These missions would travel much faster than the Voyagers, perhaps 20% the speed of light, reaching Proxima Centauri in about 20 years. Such spacecraft would carry instruments to study exoplanets, possibly even land on them, sending data back across light years to Earth. But even these advanced missions would become interstellar wanderers eventually. After completing their primary mission, they'd continue into deep space, joining the Voyagers as human artifacts traveling between stars. Over millions of years, we might populate the galaxy with our spacecraft, a growing fleet of probes and missions, all of them eventually silent but still traveling, still carrying evidence that we existed and reached for the stars. There's something poetic about this exchange. The galaxy sends us visitors like 3I Atlas, rocks from other stellar systems that we observe and study. We send the galaxy our own visitors, spacecraft carrying messages and instruments, ambassadors from Earth to whoever or whatever might find them in the distant future. The exchange is asymmetric. Their visitors are natural, ours are artificial, but both represent the same phenomenon. Matter moving between stellar systems, connecting parts of the galaxy that would otherwise never touch. The Voyagers will outlast human civilization. Whatever happens to humanity, whether we thrive and spread to the stars or fail and go extinct, the Voyagers will continue. They'll travel long after the last human is gone, silent witnesses to a species that briefly looked up and wondered. They carry our voices, our music, our images, preserved on gold, traveling through a darkness that will last far longer than we will. In this way, we've made ourselves part of the galaxy's network of wanderers. We're participants now, not just observers. We sent matter from our system into the wider galaxy, material that will visit other stars, carrying information about us and our world. It's a small contribution to the vast traffic of interstellar objects, 2 tiny spacecraft among billions of natural wanderers. But it's ours. We put them there. We sent them on journeys that mirror 3I Atlas's journey, closing a circle of exchange between stellar systems. When 3I Atlas passes back into interstellar space, it joins a cosmic population that now includes Voyager 1 and Voyager 2. The natural and artificial wanderers travel together, separated by vast distances, but part of the same phenomenon. Objects moving between stars, carrying their origins with them, connecting the galaxy through simple physical presence, creating relationships between stellar systems that couldn't exist any other way. And so, we return to where we started, but with deeper understanding. Something from another star system passed through our neighborhood. For a few months, we watched it, studied it, wondered about it, and now it's leaving, returning to the darkness between stars, continuing a journey that started long before humans existed and will continue long after we're gone. This visit was brief. 3I Atlas spent millions of years in the dark between its origin and our sun. It will spend millions more travelling away from us toward whatever comes next. The time it spent visible to our telescopes, close enough for study, represents a tiny fraction of its existence. A few months out of millions of years. A moment of connection between two stellar systems across the vast emptiness of space. That connection matters. For those months, matter from another star system was here, in our space, sharing our sun's light. Atoms that formed in a different protoplanetary disk orbited our sun briefly. Material that has never known Earth's gravity passed within a few 100 million kilometers of our planet. Two stellar families touched, separated by light years and billions of years, connected by this wandering rock that happened to pass through both systems. We're connected to distant stars, not just through physics and chemistry, not just through the shared laws that govern all matter, but through actual physical exchange. Objects from there visit here. Objects from here visit there. The galaxy mixes itself through this patient process, material circulating between systems on timescales that dwarf human comprehension, but operating nonetheless, constant and universal. This makes the universe feel less lonely. We're not isolated on our small planet, orbiting our small star in our small corner of the galaxy. We're part of a network of stellar systems connected through material exchange. Matter flows between stars, carrying information, carrying history, carrying the possibility of life spreading between worlds. The galaxy is more integrated than empty space would suggest, more connected through these wandering objects that cross the voids. 3I Atlas taught us things we didn't know. It showed us that interstellar objects are diverse, that each visitor brings new surprises. It proved that our detection capabilities are improving, that we can find these objects and study them despite their dimness and speed. It demonstrated that the galaxy's traffic of wanderers is real and ongoing, not rare exceptions, but regular occurrences that we're finally learning to observe. The visitor is fading now, receding into distance and darkness. Soon, it will be too dim to detect even with our most powerful telescopes. It will return to invisibility, to the state it knew for millions of years before briefly passing close enough for us to notice. But we saw it. We witnessed a visitor from elsewhere. We measured its properties, traced its path, wondered about its origin. For a moment, we connected with something from impossibly far away. If you found peace in this cosmic story, if these facts about a wandering rock from another star have brought you calm wonder, please consider subscribing to this channel. We explore the universe like this regularly, finding quiet amazement in the vast and ancient, helping you understand the cosmos as you prepare for sleep. Tomorrow brings another journey, another topic, another chance to fall asleep. To the gentle mysteries of science. Hit that subscribe button and join us. Leave a comment sharing your thoughts about this interstellar visitor, and let these thoughts settle gently as you prepare to rest. Now, let yourself relax. Think about that rock, small and dark, traveling through the emptiness between stars, moving at 30 kilometers per second, but patient across millions of years. It came from somewhere we can't identify, crossed distances we can barely comprehend, swung past our sun, and is returning to the darkness. It asks nothing. It expects nothing. It simply travels, following physics, existing. There's peace in that existence. Purpose without intention. Journey without destination. The rock doesn't wonder where it's going. It doesn't question its path, it simply is, moving through space, carrying atoms from its origin, participating in the galaxy's slow mixing without awareness or concern. As you settle into sleep, know that right now, at this moment, 3i Atlas is out there, millions of kilometers away already and getting farther every second. The distance grows, the connection fades, but the visit happened. We were briefly in the presence of something from another star. The universe brought us a quiet hello, a small piece of cosmic connection, a reminder that we're part of something vast and ancient and beautiful. Let that thought carry you into rest. The galaxy is full of wanderers, objects traveling between stars on journeys that span millions of years. Some passed through our system before we existed. Some will pass through long after we're gone. But this one, 3i Atlas, passed through now, during our brief moment of existence, while we were here to notice. We witnessed it, and that witness, that brief connection between our world and a visitor from elsewhere, is a gift the universe gave us for free. Sleep well, knowing the cosmos is stranger and more connected than it appears, knowing that matter moves between the stars, knowing that we were visited by something impossibly old, impossibly travelled, impossibly patient. The visitor has moved on, but the wonder remains, settling gently as you close your eyes and let sleep carry you into dreams of distant stars and ancient travellers and the peaceful, patient darkness between worlds.